Well, welcome everybody. I'm Mike Bugs, I'm the chair of Earth Science. So it's my pleasure to introduce Nathan Toke to you today. He's one of our newer faculty in the department that's really invigorated our program. He's, as you can see, an expert in actively researching fault earthquake processes. Nate did his undergrad at the University of Vermont and then went to Arizona State and continued his education, doing a doctorate there, studying processes along the San Andreas Fault that he's continuing with. He's a real asset, plug him a little bit, small group. He's bringing in external money. He's got a number of students working actively with him on some really innovative projects related to these sorts of issues and other issues involving faulting and locally here in the Wasatch Front. So we're lucky to have him, and it's going to be a pleasure to hear you speak.
Cool. Okay, this is on. All right, so I know half of you, and I probably should have, and for you half, I probably should have geared the talk a little bit differently. But the other people that I don't know, are you science majors or just kind of general education? Because that's kind of what I was hoping to gear this talk at. And the title is, as you can read, The Misbehavior and Undesired Interactions of Faults, Implications for Earthquake Hazards, Here and Away. But I'll focus on the here. And the motivation for this talk is essentially when I meet somebody, say like my neighbors, when I moved in here and I told them that I study earthquakes, I'm an earthquake scientist, an earthquake geologist to be exact. They asked me, so, well, we live in Utah, we know there's an earthquake. When is the next big earthquake going to happen, the big one? And I don't really like that question because as earthquake scientists, we don't have an answer for when. We cannot say exactly when that's going to occur. But we have learned a lot about earthquake science over the years, which can benefit society. And the point of this talk is to show you some of that, and then also say, what can we say that will help society? We can't say when, but what can we? So, I guess I have that here. So, I want to just go through a couple of motivational slides to show off the hazard of earthquakes. So this is a magnitude 9 earthquake. Can we bring the lights down just a little bit more? In Japan, the Toke earthquake of 2011. In that earthquake, there were a lot of fatalities, about 0.05% of the population. And of course, that was mostly due to tsunami. Same year, there was a much smaller earthquake, magnitude 6.3. In New Zealand, 166 people lost their lives. Similar number there, 0.04% of the population that experienced strong ground shaking lost their lives there. And want to show this is a similar sort of situation to here along the Wasatch in the fact that the earthquake was really close to the city. Size of the earthquake is not too far off. We might have a slightly bigger earthquake than that potentially. But that's kind of an important number to think about the proportions there of people that could be affected. Worldwide, earthquakes are a pretty big concern for a lot of cities. This is a map of urban areas in black. So urban areas are those defined here as more than 400 people per square kilometer. And then seismic hazard here in the colored areas of the digital hillshade in the background there. And so you can see along all of the major plate boundaries where you have a subduction zone, along the trench of South America, you have a lot of seismic hazard. Not too many cities, but there are some that are in that red zone. If we look here in Asia, along the on the Himalayan front there, we have the convergence of India into Asia. We have a lot of seismic hazard and a lot of people. Also here in the Wasatch, you can see we have some seismic hazard, and in California, we'll spend some time talking about those areas, as well as Japan. People live where earthquakes are. This slide is one of my important ones I like to always show lately. It's from a paper by Roger Billum at the University of Colorado, and from a paper that was entitled The Seismic Future of Cities. And it shows nicely why it's important for people to worry about earthquakes. This is a graph of cumulative earthquake fatalities through time. So this is over basically a lot of human history. So there's BC, AD, and there we are today. And so here's population growing with time exponentially, and cumulative earthquake fatalities go up. But how does it go up? How would you say that it goes up? Does anybody want to point something out there? Is it smooth? It's steps. Yeah, so these are big jumps, and if we look at the cumulative fatalities in millions, we can come over here and we say, okay, we're at like 1.8 million, and then all of a sudden we're over 2 million. All of a sudden in this 1 year, what happened? Well, an earthquake struck a city, and that's the point of this article, is that there are a lot of cities with earthquake hazards, and when those earthquakes do occur, these big ones, if you will, as people like to call them, the big one for that city happened, and so we had a lot of loss of life. It's variable in terms of how big the earthquake is, earthquake magnitude. So like the New Zealand earthquake, magnitude 6.3. Actually, this should be a little higher. It should be 160 foot. And then Japan, that's off too. I don't know what's going on here. It should be 20,000, magnitude 9. And then so you can see the magnitude 9 earthquake, a lot of people lost, but some larger magnitude earthquakes, not very many people. And that's because, why? Well, some of these earthquakes strike where people don't live. If we have small earthquakes and a lot of people lose their lives, that's because of a social aspect. We haven't engineered or built those buildings to meet the hazard. So we probably want to know, and this is what my neighbors want to know, what about the Wasatch Fault? Where does it lie on this graph? And so we might have earthquakes somewhere between 6.5 and a little over magnitude 7, so that would put us up in here. And then based upon analyses that have been done related to activities like Great Utah Shakeout, which occurs in April here, there was a national shakeout in October. Those activities and modeling efforts have shown that we should probably expect to see, based upon current infrastructure, loss of life in about this region, about nearly between 1,000 and 2,000 people, over a population of 1 to 2 million people. And so we're a little bit higher. If you do that ratio, it's not 0.05% of the population, it's more like 0.1 or maybe even approaching an order of magnitude not as good as, say, New Zealand. So we would like to lower that down here, right? And then make us all happy, right? So we'll talk a little bit about how maybe that can occur. Okay, so where we're going to go from here is talk a bit about fault segments and this idea of a characteristic earthquake, which is a lot of where the idea of the big one that the public has comes in. And turns out that idea, characteristic earthquake, was essentially born here and based on data collected by earthquake scientists studying Utah's Wasatch Fault and San Andreas in California. And then we'll go on from there to talk about how maybe this characteristic idea, that really simplistic idea that faults have this big earthquake that is pretty repeating through time and maybe very similar through time is probably not a great assumption, and we'll see how some earthquakes are quite heterogeneous and dynamic. And so we'll look at some examples from Japan and California. And then we'll look at some work that Larry here in the audience has helped out a little bit on, and some other students here related to our field camp this past summer, looking at the Provo to Salt Lake City segment boundary along the Wasatch Fault, and show that earthquakes don't really care too much that there's a segment boundary there and they rupture on through. So we're not going to predict and date earthquakes, so the goal of this talk is to say what should we ask as the public or the community at large, and we should really be asking what data do we need to answer some questions about mitigating earthquake hazard. And that's not timing, it's preparation beforehand. Okay, so what is a fault? So here's this little cartoon diagram. There's our fault as it projects here into this plane that would cut through into the earth, and it would go along through there at depth 2. And then an earthquake, we have what's known as the focus or the hypocenter, where the earthquake starts moving. Okay, so why does it start moving? So there's tectonic stresses that are basically flexing the rocks elastically, the crust. Think of it as like you're putting pressure on them. They're building up that pressure and they're bending off to the side here, bulges up, bulges up. Eventually, just like keep pressing on your fingers, it's going to snap, right? And that strength of the fault, this weak point in the crust, is exceeded and the fault slips. Now the question is, does it just slip a little bit? It's a little earthquake that just basically is like a point source, like right there? Or does it become a big earthquake, the big one, where it slips down, up, and along the fault for a long ways? In this case, in this cartoon, there have been big ones, and we can see that because there's a fault scarp, which means that it has moved a lot through time over a wide area and had a lot of displacement. But not all earthquakes are big ones, and not all faults are big ones. So there's a lot of simple models that have been developed to explain how faults form, and this is just an example of one of them. That is that, say, basically you've got a crack that's developing as stress is being applied to some body, and say, pretend it's the crust, or some rock within the crust. And so that crack may grow and have displacement and propagate across it. So we don't have scale on here, but you can think of it as something really small, or maybe the size of this room. But through time, those cracks will grow, and they may start to feel the nearby cracks and link up to become bigger faults. And maybe we see some hints of that if we look at the Wasatch Fault. So this is a map of that from a paper by Krista Ross of the Utah Geological Survey, and shows faults in black. So there we are down by Nephi, and there's the Wasatch Fault, and here in the Provo segment, there's the Wasatch. In Salt Lake, there it is, Weaver on up. And so what you see there is that some of these areas, the fault is mapped pretty continuously. It looks kind of straight. Maybe it's its own little section of the fault, or one of these faults that is then linking up with the neighbor to form this fault zone, or the Wasatch Fault Zone. And so this kind of, Wasatch was a nice analog to show these kind of breaks and segments that might help to control how faults break and in earthquakes. And turns out that's what was discovered, at least, or talked about in 1984. A paper by David Schwartz and Kevin Coppersmith, really famous paper entitled Fault Behavior and Characteristic Earthquakes, Examples from the Wasatch and San Andreas Fault Zones. And so if we read it, it says, this abstract says, paleoseismic data from Wasatch and San Andreas fault zones have led to the formulation of the characteristic earthquake model, which postulates that individual faults and fault segments tend to essentially generate essentially the same size or characteristic earthquake, having relatively narrow range of magnitudes near the maximum. And characteristic earthquakes have been used a lot of ways since then to say basically, it's almost like this idealized model that we put up there to say, okay, now we've got a model to pick apart, and that's what we do in science. Does this really work? And what's the evidence for it? Well, they saw the fact that along the Wasatch, there's trench sites they've dug, these little sites here, where they've dug across the fault and basically looked for evidence of past earthquakes. And it turns out almost all of them had really similar sizes of displacements from motion along the fault, and therefore probably were similar in size of magnitudes. And similar sorts of things are seen on the San Andreas Fault. And even more than that, if we look at earthquake magnitude, so magnitudes increasing in this direction upon each of these graphs, and then the number of earthquakes, so is there a lot of earthquakes or a little for that magnitude? So low magnitude earthquakes, we have a lot. High magnitude destructive earthquakes, we have a little. This is known as the linear Gutenberg-Richter relationship, where frequency of earthquakes decreases with magnitude. The characteristic model follows that up until some high magnitude earthquake, at which we would expect more earthquakes to occur. It's above the frequency of the linear Gutenberg-Richter relationship. And some fault simulation models have shown this to be the case. So there is a basis for it in physics, not just in observations of paleoseismic data too. But is it really the same repeating earthquake? Is it a characteristic earthquake that occurs? That's a different question. Oh, by the way, this paper received like over 1,100 citations according to Google Scholar. Okay, so let's travel to the San Andreas Fault. The San Andreas Fault is basically the plate boundary between the Pacific and North American plate, running from the Mendocino Triple Junction, Northern California, down through into Baja in the Gulf of California. There have been two historical great large earthquakes. One is the 1857 earthquake, which is about a magnitude 7.9 or so, which ruptured from near Parkfield down to the southeast, east of Los Angeles. This earthquake was felt widely throughout California. Didn't do a lot of damage because Los Angeles at the time had about 2,500 people living there. And so there's some written record about it, but it's not the magnitude of record that we have for the 1906 earthquake, which ruptured to the north and caused a lot of destruction of the city of San Francisco via fires. Here's a picture of a fault scarp or a tear in the ground as the earthquake displaced the ground surface. In between these two ruptures is known as the central creeping part of the San Andreas Fault. And so this area is one that I've been working on a lot, and then some students have been involved with here for UVU. We've been trying to look at that site as that area as a paleoseismic site. Even though it creeps today, it creeps at a really high rate, nearly the full motion that we'd expect across the San Andreas Fault from elsewhere. So we might not expect there to be earthquakes there. And that would kind of follow this kind of characteristic sort of model if we said that. But we've been trying to test that. Are there any earthquakes there that would put it outside of this mode of slip that's all via creep? Why is there fault creep there? There's been a lot of work into trying to figure that out. For one, there's different geology there. So a lot of the San Andreas Fault is juxtaposing kind of crystalline granites across the fault zone, whereas here we've got what's known as the Franciscan assemblage within the fault zone, and that's like this metamorphic assemblage which has a lot of minerals such as serpentinite, which may alter to talcs, and we've got other alterations going on, going to clays. Clays, talcs, these things have low frictional properties, right? They have low friction. And then also within the fault zone here, we may have really high pore fluid pressures, which would be opposing, the normal stress that would be acting against the fault. And so basically, it's pretty weak. And so it can, we think, accommodate this kind of stable sliding behavior without earthquakes. But there have been earthquakes, just not big ones. So this is a map showing kind of estimated epicenters of historical moderate magnitude earthquakes, these stars, across the creeping segment here. To the south, there haven't been any of those since 1857. This is Chelan, that's the part that ruptured in 1857. And the part that ruptured in 1906 is to the north of here. So these earthquakes, there was another one recently, 2012, my birthday last year, really close to where we've been working on the Central San Andreas Fault. And here, over the top of that, I'm going to put now aligned here is the creep rate of the fault. And so here's Parkfield. And so there's some fault creep there, like 10 to 20 millimeters per year, 1 to 2 centimeters. And then in the center of the creeping segment, it's like 3 centimeters per year. And then it tails back down more gradually to the north. Okay, this is this Dry Lake Valley trench site that we're going to look at in a minute. And so we've been looking for earthquakes on the creeping segment. Parkfield, this area, which transitions from the creep down to the locked part of the fault, which ruptures in, at least historically, in big earthquakes, was the site of this earthquake prediction experiment run by universities and the U.S. Geological Survey. And basically, what they had seen is since that 1857 earthquake, there had been a series of earthquakes, 1881, 1892. Every 20-ish years, there was another earthquake, and they were all about magnitude 6. So we start to say, well, that kind of fits our idea of this characteristic earthquake. And so they set up a lot of monitoring for geophysics and things to see, was there any precursors to the next earthquake that would tell us when that big one, or this segment's big one, is going to occur. The earthquake didn't occur till 2004, so it wasn't really along this linear trend with time. So the timing wasn't quite there, but it was magnitude 6. Now, what did it look like? Seismology is able to resolve, and geodetics, kind of what happened on the fault surface itself at depth. Where did it slip? We can see as geologists where it slipped on the surface of the landscape, but seismology and geodetics can start to picture where it happened at depth. And so let's look at the 1966 earthquake and compare it to 2004. So here's 1966, and this is the northwest, so it would be up here, and then the southeast down here, and then depth in kilometers, so we're going down 10 kilometers depth. Earthquakes sometimes rupture quite a bit deeper than that. But the star is where the earthquake started, the hypocenter. And so in 1966, it started to the northwest, and then the earthquake grew out from there, and it had these patches where it slipped a lot, slip accumulation. And so it slipped mostly to the southeast and near the surface. Compare that with 2004. The earthquake started on the southeast, and most of the slip was at depth and to the northwest. Okay, so they're not the same earthquake, right? It's not a repetition. It's not exactly a characteristic event. In fact, you might start to wonder if 2004 is just filling in what didn't rupture in 1966. But they were similar magnitude. Okay, so let's look at some more examples of maybe some things that might be not intuitively expected. So this is a similar graph as these previous two, but for the Japan earthquake. And so it's plotting the fault. And so in Japan, I think you've got the island here, and offshore is this trench, and so you've got this compression between the two, and there's a fault here. And so we're looking at this plane along the fault plane. And so you have to take that image and like rotate it at an angle. And so this would be the hypocenter of the earthquake, and so that's where it started. And what the graph shows is distance, hundreds of kilometers on the top, or kilometers on the top, so 250 kilometers of rupture, greater than that on either side, so it's a really big earthquake. 500 to 600 kilometers long, and then over 50 kilometers deep along the fault plane. And then if we look at the colors on here, we see slip in centimeters. So this red patch is over 3,300 centimeters, so 30 meters of displacement. So it'd be like cutting this whole room in half. Okay, so it's a lot of motion. It's a lot different than Parkfield earthquake, where we're experiencing slip of 40 centimeters for magnitude 6, so magnitude 9. Okay, and then the last thing that this shows that you can see anyways are contours of time, where the earthquake was rupturing out with time. So it started right here, but it grows. And so it's growing faster in this direction, that's why this contour bends out. And then other places it's growing slower. And so you start to see this earthquake as this dynamic process where it's starting here and it's moving around. The fault is moving in different places. And so it's moving here at the same time it's moving here. The earthquake is growing. And turns out the earthquake, while it started down here, had most of its slip near the surface. And which is a little bit unexpected because this is an area where the fault creeps in between earthquakes and creeps at a pretty high rate. And so you would think, based upon how we kind of simplistically think about faults, is that, okay, if it's moving, it's accommodating all of the stress, the motion between earthquakes, why does it then slip so much more during earthquake 2? Isn't that a problem? Does it create some sort of issue? And so, there's been some work into that recently, and it has helped to lead to a lot of investigations of the San Andreas fault, which is a different situation because it's not a reverse fault, it's a right lateral strike slip fault, but we do have this sort of creeping area in between. And so there's this question, well, so in this case we can rupture through that creeping area and have actually really high rates of high amounts of slip. And what about here in Central California? Couldn't that happen too and have a wall-to-wall rupture? Well, physics-based numerical simulations say that yes, okay, that does occur in these numerical earthquake models. But we are wondering, can we find that evidence on the ground in the geology? And so this is this Dry Lake Valley site, which is like in this heart of this creeping segment of the fault. And so we basically dug trenches or holes in the ground across this sag pond, or this structural depression in the fault. And it gets filled in with sediments, which is why we chose to dig there, because sediments are young and they would then get broken by activity along the fault. The character of deformation in these trenches is really widespread ground cracking. And we did not see any evidence of, like, you say, like 10-meter displacement with giant cracks in the ground. We didn't see anything like that. But we did see, like, maybe we pick out that little dark spot right there. And there's another one right over next to it. These cracks, there's cracks that are open just a few 5 centimeters or so, or a hand width open, and then filled in with sediment. And so we start to wonder why or how those occurred. And if we look at the creep that occurs there, which is pretty high on any given year, just the annual creep doesn't really produce those sort of cracks in the soil. It does if you go across a roadway where the ground is coupled together. It creates like a couple centimeter cracks, but not in the soil. And so these must be related to either some sort of moderate magnitude earthquake and accelerated creep, or perhaps some bleeding in of slip in larger earthquakes from nearby parts of the fault. Okay, so let's go back to the Wasatch and look at another segment boundary. And so here we are, we're going between the Provo segment of the Wasatch Fault to the Salt Lake segment. And we're going to look at Traverse Ridge, or Point of the Mountain, whatever you prefer to call it. And this part where the Wasatch Fault, shown in yellow here, just basically makes a 90-degree bend. And it does it again at the other side on Salt Lake segment. Okay, so we're going to zoom in there. And we've had this luxury of this beautiful data set called LiDAR, light distance and ranging, which provides, basically it sends, like, you fly an airplane over the landscape, you're shooting down a light pulse, and you're getting pulses back from the ground, reflections, if you will, and some of those pulses like hit the tree canopy, but others will make it all the way to the ground because the trees are porous, essentially with leaves and such. And so we get data of the ground, data of tree canopies. Some people use LiDAR to study trees, but as a geologist, I'm interested in what's underneath. And so we can get rid of all of that. And we can just see the landscape for its soils and rocks. And so the Wasatch Fault comes in right here, and you can kind of maybe make a sense that there's all these kind of lineations that are running, here's north up, kind of east to west through here. That's the fault zone. So we're going to zoom into here, and these lines going the other way, and see what those are. Turns out these are, here's a scale, 0.8 kilometers, so there's like half a kilometer from here to here. These things are like half-kilometer long trenches, holes dug in the ground in 2006. They were done for a geotechnical study. The area was slated for potential development, and they needed to do some geologic analyses. Development never took place. Trenches were left open. They were dug, like I said, in 2006. This was before the LiDAR, which I just showed you, which was 2008. And if we look at this image as a group here now, where would you guys put the faults? Anybody over here that's not a geologist? I'll run over and see if you can do it. You guys want to try? Sure. Okay. So the red button there. Along there. Okay, yeah. So yeah, you see those ridges and things. That's good. That's what I at first glance I might say too. And you start to wonder, so how did they decide where to put the trenches? And I think they probably used pre-existing geological mapping. And so there is some of that existed at the time. And this is what shows for faults. And so you weren't far off with one trace. Okay? But then there are these others that are on there. And I'm going to put my pointer on this one right here. Okay? So I'm trying to hold it in the same place. I'm going to click at the same time. That was right there. Okay, so I'm going to go back. Now where do you see the faults? Actually, there. That was right there. It's a little bit over here and here. And unfortunately, some of the faults are actually right off of the trenches. Right? The LiDAR is a great tool. And so when we went out there this summer, we used it. The field camp, they mapped these faults, and then we decided where we're going to kind of re-expose the fault zone in these trenches. Unfortunately, the geotechnical people, when they dug these, it's 7 trenches, half a kilometer long each, so that's 7 kilometers to look at. And I don't know what sort of time span they had to work with, but it probably wasn't a whole year, because that's what it would probably take to do that in a good way. So they, turns out, probably didn't see some of the features that we did. They didn't expose them, and that may be because some of where the faults are is actually slightly off from where you might expect them to be, but they're right here in this trench. And so we're going to zoom into this spot right here and look at what it looks like. And so this is a picture of what we exposed, and you probably can see, even if you're not a geologist, that there's a big contrast between what's over here and over here, right? And so let's add a little bit, and I would argue there's a real nice contrast right there and there, and maybe another one here. So that's our fault zone. And so we have volcanic rocks on one side. These are like 30 million year old volcanics. And then on this side, we have essentially material that's shed off of this hill slope. And so some of it is kind of just clayey and kind of red down here, and some clasts, bigger rocks. And then up above, it's very dark and organic. It looks like a nice topsoil. Within that upper soil, that really organic stuff, we were able to distinguish some horizons. Here you can see there's clasts up in there. It's these bigger rocks kind of draped through there. But also if you scrape it off, you can see that the finer material there is slightly more gray, and then it is dark down here. And we saw this in 3 packages. And so we interpret this as individual times when the fault has slipped this side down. And so these may represent individual earthquakes with 0.5 meter to nearly 1.5 meter displacements of the fault at this spot. And so here's another example from the other scarp. And you again see these packages of dark material. And together, it's about 1.4 meters of displacement across there. If we were to draw a profile across the landscape, the green line there, This is what it looks like. We have a hill, it drops off, that's a fault zone. It rises back up, hill, falling fault zone, rises back up again. This trench is located roughly here, so the fault would dip in there. And the other one was there. Put them back up here. Oops. So we are looking at this one right there, and that one right there. Okay? Displacement across those, if we assume that these surfaces once lined up, would be about 24 meters here and 19 meters, or about 43 meters of fault motion since whenever this landscape was constructed. We don't know the rate of slip right at the site for the fault, but other places say that it's about 1 millimeter per year. So it may be about 45,000 years old, this landscape. So what we had for estimated fault slip was somewhere between 0.5 meter and 1.5 meters almost of motion. There's a lot of data from earthquakes that have occurred around the world, fault ruptures. And people have gone through and correlated the amount of slip that you have in an earthquake in terms of displacement at a site versus the length that the fault ruptured for. And so these are basically empirical relationships, taking this estimated fault slip from our colluvial ledges and making them into estimated fault rupture lengths. And so with those relationships, the best fitting line we use, we get about 54 kilometers for the big displacements and about 24 kilometers of rupture for the small ones. Okay, so now let's go zoom back out. Here's the site that we were just at. And let's see what a 24-kilometer long rupture would look like. The triangles are nearby paleoseismic sites that were pre-existing. So here's a 24-kilometer long rupture centered at the site. And there's a 54-kilometer long rupture centered at the site. Interestingly, and probably fortuitously, the 54-kilometer long rupture, if you center it at the site, coincides roughly with this little step over here at Provo Canyon, where the fault jumps over and the mountain front comes out. And then here in Salt Lake, there's a similar sort of relationship up there. Whether or not that is the controlling factor for these rupture lengths, I won't say that. But what we can say from the size of these ruptures is that the ruptures likely span in or rupture into the neighboring segments. It's not just a little bit of a slip on this intermediate fault in here. It's going through to one side or the other or both. And so we should be able to see that information in these other nearby trenches in terms of the timing of when these occurred. The issue with that, and so here we are at the segment boundary. There. And there's Salt Lake, Provo. And so these are earthquakes that were seen on Provo. So there's one 600 years ago, and you can see this graph assumes a very characteristic-like behavior, where the whole fault segment ruptures. Of Provo, 600 years ago, plus or minus 350. And then 2,800 years ago, 5,300 years ago. Salt Lake, we see a lot of earthquakes, but not very many recently. And so we're wondering, the earthquakes that we saw in these trenches, and I guess I shouldn't have done that, these things, where do they fit on there? What is the timing of those things? Is that youngest earthquake that we see in there, is that this one? Or is it this one? How often do those earthquakes link up through the segment boundary? Or are they different ages altogether? Because earthquake geology, we're seeing the evidence that we have. And so if there's no sedimentation, then we don't recognize an earthquake necessarily. Normal faults would get a little bit better there, in this site in particular, right? Because we're actually displacing, so I'm contradicting myself here, we displaced volcanic stuff that's 30 million years old, so there's been no sedimentation really since then, but because we created a slope, we then erode new material over the top. Okay, so we do have some dates potentially coming. We've got samples from those sites. We have to send them off, and hopefully we'll get to see where do these fit in. But I guarantee you, no matter what we find, we're not going to be able to say exactly, convincingly, that this earthquake is this earthquake. Because the plus or minus on these things is huge. Conceivably, the real age of this earthquake could be up here, and this one could be down here. Are they really the same thing? So we're not going to get exactly the timing of earthquakes, but geology brings in a lot of other things. We start to learn about, do earthquakes rupture for longer distances? Are they bigger earthquakes? Do they cause more shaking? When they do cause shaking, what happens? One of the things that happens often if you have a shallow groundwater table is liquefaction. Basically, you're shaking these loose sediments that are nearly saturated in water. It makes them saturated, and the pore pressures in the water get so high that basically it acts like a fluid. And so here, this car in New Zealand basically sunk with quicksand into there. As soon as it stopped, it's then frozen in place. Shallow liquefaction can also produce shallow and flat landslides known as lateral spreads, which can cause a lot of devastation to the ground surface. Or you can have whole subsidence of buildings. Where is this liquefaction likely to occur in Utah? Those maps exist. You probably know if you're in an area where your basement floods all the time that you're probably in one of those areas. But you can check to make sure that you're right on that, so you can know that information. What else can geology tell us? Well, you saw that seismic hazard map for the world. We can produce those in more detail for local areas. So say, for any given location, like the Wasatch Fault, really idealized cartoon, given a time span that we're looking to plan for, do we worry about the next 50 years or 150 years? That's up to the planners. And then how rare of event do we plan for? Do we plan for like a big one, a really low probability event, 2% chance of happening? If that's what we're interested in knowing, what's the worst thing that could happen? We can find that out. So we can consider all the known faults nearby and ask, could it have an earthquake in that time span based upon the recurrence rate that we see from geology? If so, then we go on and calculate what would it be in terms of an earthquake size, how much energy is being released, and then how is that energy radiated away from the fault, producing shaking. Shaking is generally closest to the fault and radiates away and decreases or attenuates. But that's a really simplistic way of looking at it. And here's an example of that. This would be, and I know you can't see the contours on here, but just give me a second. So this would be a 2% probability of exceedance in 50 years of ground shaking levels for Utah County. And so here's UVU, and the contour that we're by is between 1.2 and 1.1 Gs, or 110 to 120% of gravity, for 0.2 second spectral response, so stuff that would affect small buildings like the homes that we live in. So that's a lot of ground shaking, right? And it's not something that we really want to deal with, but we may have to. This is based on a pretty simplistic model for how this ground shaking radiates away. There are some more dynamic models which aren't treating the fault as like this uniform rupture, but rather maybe the fault ruptures from one side to the other. Or maybe we can put in some different information about the geology. Where are the different sediment types and rock types? How do those shaking responses map out through the landscape? And so here is the fault. And so surprising to me, there's some places that are in between the fault. In this particular scenario, now this was for a particular earthquake, which I actually am not remember if it ruptured from south to north or north to south, but it did one or the other. And you can see based upon that and the way they modeled it out, there's areas which have really high shaking and areas that are real close to the fault that don't. And so potentially, if we could run all of the possible scenarios that would be likely, and then we know what earthquake did happen right afterwards, we could know pretty well what probably happened on the ground. Of course, we have other things like systems whereby the people who felt the earthquake can report it, and we have instruments that record ground shaking. And all those things go into emergency response. Okay, so I gotta wrap up soon. I want to just point out a few things that have been really positive outcomes from using what we know about geology to kind of mitigate potential problems from earthquakes. So we're looking at the Alaskan oil pipeline here, and that's the Denali Fault. It goes right through that forest there. So here's the Denali Fault as it goes through the landscape in Alaska, and here is the oil pipeline. It was built in the 70s. It takes about 17% of our domestic oil supply. And it was known that it crossed an active fault when it was built. And so they conducted geologic investigations. Those investigations were to look at what happened in the past, to see what could potentially happen in the future in terms of the size of displacements, size of energy released. And so the geologic studies show that it was probably capable of producing these big magnitude 8 earthquakes with 7-meter displacements, 20 feet. And it did happen in 2002. And the pipeline, well, this is after 2002, it's fine. What they did is they built it on rollers, right? And so the fault moved and the landscape on this side and that side moved, but the pipe just sat there while the landscape rolled past, okay? And so it's really pretty, in a way, it's a simple engineering solution to prevent a huge disaster. And there's other things you need to worry about other than fault displacement, of course. Don't site it through an area with a landslide potential. But the point is that fault rupture does not equal pipeline rupture. And so we have a lot of other pipelines, especially in urban environments like here on the Wasatch, transportation ways, waterways, communications, electricity. Can't we design those things that cross the fault in a similar way as the Alaskan pipeline and prevent those things from having major catastrophes in a future earthquake? In Los Angeles, I just saw a talk on this in September at the Southern California Earthquake Center. They're really taking this to heart, and actually some observations from New Zealand as well to try to redesign some of the water crossings for the LA area that come across the San Andreas Fault. So LA receives most of its water from the Colorado River, Owens Valley, Central Valley, and all those waterways have to cross the fault. A lot of them do so in tunnels. And so the tunnels potentially have the risk of being cut off in an earthquake if the fault slips so much that it's past the width of the tunnel, or collapsing, or both. But the geology can tell us how wide do we need to build these tunnels. And so we can do that, and they may need to be revised, was what's coming out of that talk that I saw. They need to be widened in the zone of the fault. But then the other thing is that we can convey the lifelines through these tunnels using I actually don't know the material, HDPE pipes. In New Zealand, these were the gas lines that were used, the type of material that was used in Christchurch. And there was tons of liquefaction and ground subsidence, and these pipes really got reefed on by all that ground motion. And they had very few failures, really few failures. And so they think there's a lot of promise for combining our knowledge of giving these lifeline crossings enough space, combined with the ability of these things to withstand collapse and getting torqued around to potentially not completely cut off supplies. And so we can also do some more planning. If these terrible things happen, then what do we do? Refineries, dam collapse. Really, what you don't want to think that these things are going to occur, and we try to engineer them so that they won't. But what if they did? There should be contingencies for when we know something like that occurs, what do you automatically have happen down here? That stuff should be practiced ahead of time. And then finally, early warning. We could potentially, even though we don't know when the earthquake's going to occur, we can know that it occurred before it gets to us. So, an example of Salt Lake City, say there was an earthquake that started right there. And it's about 60 kilometers down here in Provo. P waves, which are the first waves that arrive in an earthquake, go about 6 to 8 kilometers per second. S waves, 3 to 4. These are the damaging ones, S waves and surface waves. And they're slower because a lot of their energy goes into side-to-side motions, whereas the P waves are directed in the line of travel, so they're fast. So it's going to take 10 seconds for a probe to feel the earthquake after this Salt Lake City earthquake started, and it would grow or it'd become a bigger one. And then for the surface waves to get down there, it could be 30 to 60 seconds. So you may feel it and have 10 seconds before you get the really destructive waves coming through, and so that's enough time to get under the desk or something, right? But if we also, which we do, have instrumentation all around this area, those instruments are going to feel it even earlier, and they can send out a signal, right, via fiber optics or some sort of electronic signal, which is faster than these seismic waves, and so we get a few more seconds out of it. And so in Japan, they do have those sort of early warning things. In Los Angeles and California-wide, they're trying to develop them now. Good question is this potentially a good idea for us? You could link them up to automated contingencies where you could shut down sensitive things, so nobody has to actually press a button, it just automatically occurs, and potentially, maybe save some power plant or something like that. So lastly, we have a lot of tools to figure out what could happen, and communities can do it if we can get some people to run these models using some of these GIS tools that have been developed by FEMA. Someone's called HAZUS. It basically is a way to mingle all of the lifeline data, social data, and the hazard itself for floods, earthquakes, etc. And so we have the data from the geology and the geophysics. We've got assessment tools from HAZUS and experts that are good in that. And then the technology, engineering-wise and warning-wise, is there. We're just not using it probably as well as we could. So we don't really need to ask when it's going to occur, but what have we done to prepare for it is the question we should be asking. And so when people ask me that, I try to say, well, what have you done? What are you doing in your personal lives? What has the community done? And it's something that I need to do better too. There's some resources to educate yourself. Putting Down Roots in Earthquake Country is a publication that's developed here for Utah, and there's other ones for California. It tells you what you can do in your home to make sure it's more survivable in an earthquake. There's lots of information about where the faults are, where liquefaction may occur, where it could be hazardous. And there's engineering resources out there too. So I'll stop there and take any questions that you have in the next couple minutes. Questions? Yeah, go ahead.
Where are those trenches located? It looks like you're pointing to the mountain.
Yeah, so those trenches are basically, you know where Corner Canyon is?
Uh-huh.
Yeah, so up above the mountain biking area in Corner Canyon, just off of the Jacob's Ladder Trail.
Oh, cool. I think we better keep moving.
Okay.